And welcome again as we continue our path through Chapter 4. This lesson we're going to be looking at 4.2. I expect this lecture will be a bit shorter just because there's not a whole lot of material in 4.2. Really the only significant thing we'll be looking at is yet another application of exponential functions. Section 4.2 is about the natural exponential function. And that is based on the number e. The number e is a special number in mathematics. It's an irrational number, that's why we need a symbol for it. An irrational number, if you'll remember, is a number that has an infinite non-repeating decimal. Pi is one of those. But e is another one. Also, all of the irreducible roots, like the square root of 2, are irrational numbers. But in any case, we give irrational numbers that have special meanings for us or special purpose to us. We give them specific symbols. So in this case, e is going to represent a single number. And to figure out how we find e, we look at the compound interest function, which, if you'll remember, a equals p times 1 plus r over n to the nt. Well, if I set p and r and t all to be 1, I will get a equals 1 plus 1 over n to the n, as we have here. Now, if you take increasingly large values of n, like 10, 15,000, 8 million, 3 billion, etc. And it's not hard to do that. You can do it in your calculator. Just take larger and larger values and look at. But what will happen is more and more decimal places will stay the same. Like the first one you do, when you do 1, you get just 2. But you'll get, soon enough, you'll start having every single value you get will have a 7 as your first decimal place. Then every single value you get will have a 7-1, then a 7-1-8, then a 7-1-8-2. If you go far enough, you'll eventually reach the maximum accuracy of your calculator, which is 9 digits, so it would stop about right here. 2.718281,828. But you can see here it's worked out to 20 decimal places. Eventually, if you plug in large enough values of n, all of these numbers will stop changing. And it'll still be, except maybe the 6. They could have rounded the 6. But the numbers will keep locking into place as you take larger and larger values of n. So, it's an irrational number, so you can't write all of it. But like pi, you can approximate it. I usually think about e as it's about 2.7. So in any case, here's the number. It's not hard to find a decent approximation for this. You don't have to go through this process at all because your calculator has it, because it is such a useful value. If you look at your calculator, you actually have e in 2 places. It is above the division sign. See? E right there. Do second division. Gives it to 9 places, like I said, 2.718281,828. You also have it right above the ln function here. We'll talk about ln and log, by the way, in the next video. But for right now, you can certainly use e. And this is a quick key for e raised to a power. So, I mean, e to the 1 would just be e. Not bad. There you go. But say, if you want to do e to the 5, it's between 2 to the 5th, which is 32, and 3 to the 5th, which is like 243. So yeah, that gives you powers of e. Generally, I use this function a lot, but I mean, it doesn't matter. I mean, if you wanted to do e to the 1 using this function, it would be perfectly acceptable, or e to the 2. You get the exact same values no matter which function you use. It's just a quick key. Like, I don't really need a square key. It's just we square things a lot, so they put that on there. Alright. So what are we going to do with E? I might as well graph it really fast. Oh, actually, graphing E wouldn't be that interesting, but graphing the exponential function with base E would be. So this is the natural exponential function, just e to the x. It's not significantly different than any of the other exponential functions, like 2 to the x or 3 to the x. It still has the same basic shape. We look at the graph of e to the x, y equals, I might as well plot it on here, 3, 4, 5, and then let's do e to the x. It just looks a lot like the other ones. These go up slightly slower than 3dx because 2.7 is slightly smaller than 3. So not much different there. Honestly, the best properties you get out of this function, edx, come from calculus. It's a very useful function in calculus. But even in algebra, there are some nice things about it. One very nice thing about it is we'll see in 4.6 the standard model for exponential growth or decay is based on this function, edx. So that'll be cool once we get there. But for now, we are going to use it for for interest. And specifically, we're going to look at interest compounded continuously. And probably the easiest way to think about this is that it's what happens to the compound interest formula as your number of times compounded, goes to infinity, as interest is calculated an infinite number of times. So your interest rate, like 12% in our original problem, $100 at 12%, your interest rate would be divided up into an infinitely small pieces, but then you would be adding in interest an infinite number of times. How does that interact? Well, basically the effect is you're always adding in interest, but just in very small amounts. Well, how does that affect? Not a lot different than straight compound interest. Generally, say, you will never find a lot of difference between compounding, say, 365 times a year and continuously, which is infinite. There is some difference, but it's very small. Generally, once you get past like 4, there's not going to be very much difference between compounding a finite number of times and compounded continuously. But here's the formula. It's the amount after time t in years is the original amount times e to the rt. All the same values, it's just we don't have n in this case, because we know what n is anyway. It would be going to infinity. So, let's take our $100 at 12% over a year. I believe the values we had before, if I think about them, we had 112 for simple interest. We had 112.55 for compounded quarterly. Let's see what we get for compounded continuously. So we would have 100 times e to the, we had 12% interest, so 0.12, and then times 1, so it just beats up 0.12. Yeah, we end up with 112.75. So a 20-cent difference. Not a lot of difference, but a difference nonetheless. We'll look at a problem from the book, but honestly there's not a lot left to do in this section. we're going to look at problem 23 on page 357. And here we are. So a skydiver jumps from a reasonable height above the ground. The air resistance she experiences is proportional to her velocity, and the constant of proportionality is 0.2. It can be shown that the downward velocity of the skydiver at time t is given by this. Notice all of this information just built this equation, but we haven't really talked about how. Well, we'll learn how to build this type of thing in 4.6. Right now, they're just giving you all the given information that would have been needed to actually build this. In any case, we don't care about any of this. They gave us the function. Find the initial velocity of the skydiver. Well, the initial velocity would be the velocity at time 0. So that's easy enough. V of 0 would be 180 times 1 minus e to the 0, because negative 0.2 times 0 is still 0. And that's just 1 minus 1, so this is just going to be 0. Because 180 times 0 will be 0. Find the velocity after 5 seconds and 10 seconds. Easy enough. V of 5 is 180 times 1 minus e to the, let's see, 5 times 0.2 would be negative 1. So negative 1 and v of 10 would be 180 times 1 minus e to the negative 2. If we do those calculations, (180) times, in parentheses, 1 minus it's e to the negative 1, or 1 over e if you prefer. 113. So approximately, I might as well do the other one too before I switch back over to this. So I'll just change that to a negative 2. Okay. So approximately 114 should be feet per second. And approximately 156 feet per second. Draw a graph of the velocity function. Easy enough. It's just a really easy way. I could just turn them off. Honestly, I'm not going to use them again, so I might as well get rid of them. 180, 1 minus e to the negative 0.2 x, close parentheses, close parentheses. And yeah, look at that for now. Yeah, I can barely see any of that, so... And the ones we saw were like 114 and 156. So let's change our window so we can see something a lot larger. Let's say... I don't really care about the negatives, so let's go 0 to... let's say 300. And I also don't really care about negative times. So I'll just start at negative 1, just so I have a little bit of a buffer. And look at that graph. The maximum velocity of a falling object with wind resistance is called the terminal velocity. From the graph in part C, find the terminal velocity of the skydiver. Well, it does look like it's leveling off, so let's give it some more room. Let's say 1 to 100. Oh yeah. So let's look at the trace. 179, 179. Yeah, it looks like it's leveling off to be 180 because it's still increasing. And then by the time we get over here, yeah, it just thinks it's 180. So maximum velocity looks like it to be 180. You can tell that just by extending the graph. Okay, that's all. So that'll finish us off on this section. Next time we will actually start digging into probably the biggest adjustment for you guys, logarithms. I have long maintained that logarithms aren't especially difficult, except in one aspect. And that is that you have to learn a new notation for them. And anytime you have to learn a new notation, you have to assimilate that into your mathematical understanding. It's like using a language. When you learn new words, they're awkward at first, but the more you use them, the better you get at them. So in 4.3 and 4.4, which I do believe we will combine, we will look at logarithms and logarithmic functions.